Homer Simpson bought himself a donut maker. Homer begins eating donuts at 7 o'clock a.m. At 7:02, Homer has eaten 8 donuts, and at 7:12, Homer has eaten 26 donuts. We need to write an equation for Homer's donut eating patterns. Part 1. In order to find the quadratic version of the equation, we took the structure ax squared plus bx plus c and plugged in the points 2, 8, 12, 26, and 22, 8 in order to get a system of equations. Then we used matrices to solve that system and took the answers from the matrices and plugged them back into the structure in order to get the equation y equals negative 3 over 14x squared plus 5 1/7 x minus 1 3/7. The original structure for the exponential equation is y equals ab to the x power, so we set up a system of equations to find b. Once we had solved for b, we found it was approximately 1.13, so we took 1.13 and put it back into the system to solve for a. A was 6.34. We took the two numbers we got for a and b and put them back in the structure to get the equation, which was y equals 6.34 times 1.13 to the x power. The original structure of a linear equation is y equals mx plus b, where m is the slope and b is the y-intercept. In order to find the slope, we use the equation y2 minus y1 over x2 minus x1 to get 18 over 10, or 1.8 for the slope. Then we took the slope and put it back into y equals mx plus b form to solve for b. b was 4.4. Then we wrote the final equation, which was y equals 1.8x plus 4.4. The structure for a sinusoidal equation is y equals a sine parentheses bx plus c plus d. A is the amplitude in a sinusoidal equation, so we found that first. An amplitude is the distance from the midline to the minimum or maximum. As you can see from the graph, the amplitude is 9. Next we found d, which is the midline. The midline is the line that divides the sinusoidal wave in half. In the graph, you can see that the midline is 17, so d is 17. Then we found b, which is the frequency. In order to find b, we just divided 360 degrees by 20 to get 18, so b is 18. Lastly, we needed to find c, so we input the point 2, 8, and the numbers we got for a, c, and d, and solve for c, which was negative 122. Finally, we put a, b, c, and d back into the sinusoidal structure to get y equals 9 sine parentheses 18x minus 122 plus 17. The structure for a logarithmic equation is y equals log b x plus c. We took the points 2, 8, and 12, 26 and put them back into the structure to set up a system of equations. Then we solved that system for b to get 1.104665. Then we took the number we got for b and put it back into the system of equations and solved for c, which was 1.04. We took what we got for b and c and put them back into the structure to get the equation y equals log 1.104665 x plus 1.04. The logarithmic equation makes the most sense in the context of this problem, because it says that Homer began eating donuts when he was hungry, so he ate really quickly, but as he grew more full, he ate slower and slower. The quadratic equation doesn't make any sense, because that would mean Homer had been eating donuts until he hit a maximum point and then threw them up. The exponential equation doesn't make any sense because Homer would not eat more donuts the fuller he got. The sinusoidal equation doesn't make sense because it would imply Homer was eating donuts, throwing them up, and then eating more donuts in a continuous pattern. Finally, a linear equation does not make any sense because Homer is not a donut-eating machine, so he cannot possibly eat donuts at a constant rate. That leaves the logarithmic equation for the equation that we're going to use. Using our logarithmic equation, at 7:20, how many donuts has Homer eaten? So we just take the logarithmic equation we created earlier and put in 20 for x because it's 20 minutes after 7 o'clock. Therefore, our equation is y equals log 1.104665 20 plus 1.04. When we solve that equation, we get y equals 3.135. So, at 7:20, Homer has eaten approximately 31 donuts. Part 2. We're supposed to apply a vertical stretch of 3, a horizontal shift of 4 to the right, and a vertical shift of 5 up to each of the following parent functions. The quadratic equation that fits these standards is y equals 3 parentheses x minus 4 squared plus 5. The sketched graph above shows a gray line, which is the original equation, or y equals x squared, and the modified one, in blue. The domain of this new modified one is all real numbers, and the range is y is anything above 5. The exponential equation is y equals 6 to the x minus 4th power plus 5. The gray line is the original equation, y equals 2 to the x power, while the blue one is the new. The domain is all real numbers, while the range is y must be greater or equal to 5. The cubic equation is y equals 3 parentheses x minus 4 cubed plus 5. The original equation, y equals x cubed, can be seen in gray in the sketched graph, where the new one is in blue. The domain is all real numbers, and so is the range. The sinusoidal equation is y equals 3 sine parentheses x minus 4 plus 5. The original equation, y equals sine x, can be seen in gray, whereas the new equation, which has been stretched, moved horizontally and vertically, is in blue. The domain is all real numbers, and the range is y is greater than 2 but less than 8. The rational equation is y equals 3 over x minus 4 plus 5. The original equation, or parent function, is y equals 1 over x. You can see it in gray, and you can see the new equation in blue. The domain is x does not equal 4, and range is y cannot equal 5. The root equation, which was originally y equals root x in gray, is now y equals 3 root x minus 4 plus 5, seen in blue. The domain of this new equation is x must be greater or equal to 4, and the range is y must be greater or equal to 5. The logarithmic equation, which was originally y equals log 2x in gray, is now y equals 3 parentheses log 2 parentheses x minus 4 double parentheses plus 5. The domain is x must be greater or equal to 4, and the range is all real numbers. All of the functions include a 3, a 4, and a 5. The 5 is always the added factor, and also a coefficient. The 5 is the one that moves it up 5 vertically. 4 is always represented as x minus 4, in order to move it to the right. 3 is the coefficient for x, except in 6 to the power of x minus 4 plus 5, where the original coefficient 2 is multiplied by 3. This is the stretch factor. One of the problems with the x cubed plus x squared plus x function is that when we expand it, there are 7 variables to find. However, Rebecca found a new way to do this by combining the quadratic and the cubic equations to get 3x minus 4 cubed plus 3x minus 4 squared plus x plus 1. Finally, we were supposed to write equations for 11 graphs. Graph A was just 1 over x, the standard parent function for a rational graph. Graph B was x squared minus 5. The minus 5 was added in order to make the minimum value and the y-intercept negative 5. Graph C was x minus 3 cubed because it was a cubic equation that needed to be shifted 3 to the right. Graph D was 2 to the x power minus 3. Graph E was linear with a slope of 3 and a y-intercept of negative 6, making the equation 3x minus 6. Graph F was x plus 2 cubed plus 3 because it was a cubic graph that needed to be shifted 2 to the left and 3 up. Graph G was x plus 3 squared minus 6 because the vertex was negative 3, negative 6. Graph H was x minus 3 squared plus 6 because its vertex was 3, 6. Graph I was x plus 3 cubed minus 2 because it was a cubic equation that needed to be shifted 3 to the left and 2 down. Graph J was 3 sine 1/2 x plus 270 plus 3 because the amplitude of the sinusoidal graph was 3 The frequency was 1/2. We needed to shift the starting point to the bottom, so we rotated 270 degrees, and the midline was 3. Finally, graph k was root x plus 2, because the graph needed to be moved 2 to the left, and it was a rational function.